Hi everyone, welcome to our first presentation session of day 2 of the Offshore Renewable Energy 4.0 conference. It gives me great pleasure to introduce our first 2 speakers from Dassault Systems. That's Mark Keating, Client Executive for Energy and Materials, and Graham Love, Industry Solution Technical Director. So without further ado, I'll hand over to both of you to kick us off.
Thanks very much, Jake. Nice to meet you all and welcome to our presentation today. If you want to move to the, yeah, perfect. Thanks, Graham. So just to introduce the presentation today that my colleague Graham and I are going to be covering. This is a transfer from an extension of the previous webinar that was held on Friday by our colleagues Annette and Audrey, which covered streamlining of project execution and construction with data-driven planning and simulation. In today's session, Graham and I will do a deeper dive in applying a digital approach to a few of the elements of early wind project development and focus more on some of the technical details. However, you can still get to the previous recording from last week as you need to as well. Okay, so just to provide you a bit of an introduction, I'm aware that some of you are new, didn't attend the webinar on Friday. So we're here, Graham and I are here to explain the digital innovation side to energy projects such as wind. We're both colleagues at Dassault Systèmes within a global software company whose vision is that the virtual world can meaningfully extend and improve the real world. And in the infrastructure and energy sectors, our customers and partners are all facing similar challenges at the moment, ensuring energy security in an increasingly uncertain world. And that involves ensuring that the energy we all rely upon for our needs can be accessed without interruption and at predictable cost, protecting against supply shocks, price volatility, or other disruptions. Key strategies to achieve it include reducing energy demand, diversifying energy sources, investing in renewable energy, improving energy efficiency, and developing robust energy infrastructure with extended and predictable lifespans. The level of investment to meet the challenges is also not insignificant and extends beyond the design and construction and well into operations and maintenance, repairs, upgrades, etc. So offshore wind, as a good example, is a highly demanding in terms of its logistics, infrastructure, harsh environments, such as distance to shore, weather conditions, and investment, but it has the potential to meet and exceed current global electricity demand many times over thanks to the vast amount of resources available at sea. The massive potential energy yields and technological advances position offshore wind as key to decarbonising electricity systems and meeting future and global energy demands. Now, what does a successful offshore wind project look like? Well, it's really dependent on a mix of technical, commercial, environmental, regulatory factors that ensure its viability, efficiency, and provide positive impacts. And we'll give a flavour today of how success metrics in wind, such as strong partnerships, optimized business models, efficient technical design, robust supply chain, infrastructure, site selection, environmental impacts, regulatory clarity and support, energy system integration, community and stakeholder management, these can all benefit from a fully digital approach. So at Dassault, we are able to realize the approach through our virtual twin technology, which we consider a game changer and allows us to think a little bit differently about how we plan, design, build, maintain, and operate assets. By leveraging more than 40 years of our experience and value in manufacturing sectors where our technology has revolutionized industry, we're now applying it to infrastructure, energy, and materials projects. Okay, next slide. Thanks, Graham. So a virtual twin approach could be anything from a fragmented set of models to a connected living virtual twin embedded across every project phase from feasibility to operation. However, as a strategic asset for replicable and sustainable performance, it consists of a science-driven and model-based, continuously updated with real-time data, integrating simulation, data science, AI, building information management systems, and enablement of risk anticipation, impact assessment, and confident decision-making, to give us confident decision-making. A great example of virtual twin approach is to de-risk early-stage investments through multi-scale modeling and multi-physics simulation, which we'll get into later. We can also deliver virtual twin experiences to secure the delivery phase of a project, monitoring global performance, and generating data perspectives that are actionable and contextualized on the key KPIs of a project. So the three pillars that we're showing here form the backbone of virtual twins: a system of system engineering, context-aware intelligent data science and AI, and collaborative platform. And today we'll be focusing primarily on systems engineering on the left-hand side. Okay, next slide. So typically we initiate a virtual twin project in the early stages with customers who may be looking to invest in a renewable energy project, and we would leverage model-based systems engineering, or MBSE, and data science capabilities to help determine the optimum parameters based around the desired outcomes. As we explore and reduce the options, we're going through the funnel from the top to bottom. We progress through the funnel, and by reducing the weakest elements, we raise our chance of success and progress from economic viability to technical feasibility to system specification. And we'll show through some examples of how that can be applied. Next slide. So here are the 3 points that we're going to go through in the presentation. We'll cover MBSE as a backbone, ecosystem modeling to de-risk external impacts, and advanced logical, functional, and multiphysics simulations to maximize ROI. And we'll give some examples of each of these. So over to you, Graham.
Yeah, so good morning, everybody. So I just wanted to give you a quick flavour of what we call 3D Experience Platform, which is where we bring together typically disparate data from the organisation into a single dashboard. And some of the topics that we'll cover today, so some of the GIS information, model-based system of systems, stakeholder management, as you can see here, enterprise modelling, which is a sidestep, but we'll talk about that, and the multidisciplinary simulations, and presenting that through the digital thread and the digital traceability, end-to-end traceability. And you can see that was presented through a single dashboard that brings all of this data together, a configurable dashboard for any user within the organisation using their 3D Experience Platform. And we'll take a deeper dive in a second with some of those topics. Sorry. So,
well, thanks, Graham. So as far as MBSE, or model-based systems engineering, which is the first point we'll go through, it's a methodology that replaces traditional document-based approaches with digital models as a primary means of representing, analysing, managing complex systems. So it's made up of model-centric. So it's model-centric. You're using digital models. It's a fundamental change from document-centric systems, and it applies to all phases of a system's life, from conception and design through to verification, validation, or even decommissioning. So a birth-to-death approach, and it works by representing the system. So engineers can create digital models to represent the requirements, exchange of information, supports analysis and validation, and allows for managing of complexity. So formalized model structure to help manage the complexity inherent in large interconnected systems that we have within these types of projects. So Graham will now give some examples.
Yeah, so we talk about model-based systems engineering, and we've got an example here of a system of systems, a system being an independent system that can act on its own in its own right. But when we connect them together, we increase the variability of those systems. We can increase the complexity of those systems. So we've got to take a digital approach, and a model-based systems approach is ideal to explore, analyze, build these environments. And here what we've got is a particular opportunity where this development organization is looking to develop a bid for a multi-renewable energy solution. And here we're browsing through a number of models that simplistically represent the different systems involved in our solution, or possible solution, our bid in this case. Here we're showing some supplier integration here, supplier integration where we've reused a supplier model that represents, in this case, the solar farm, and parameterized very, very easily parameterize these simple block diagrams that represent elements, that represent the flow of information, the interfaces that are used, and building up this system of systems in very simple, reusable block diagrams that we can then simulate. And here we're going to simulate potentially years worth of behaviors, looking at taking variability across the wind power and the solar power across the seasons, aiming to reach specific requirement. You can see the top right-hand corner of that little image there is a percentage that it hasn't been met yet as a requirement, that is in red. And we can simulate and understand when we meet these requirements. These requirements could be levelized cost of energy, the power output. We can start to play around with some values, really at the early stage, earliest possible stage, using simplistic models to understand what types of system models could meet our objectives and can be taken down that funnel that Mark mentioned earlier to the next step of analysis. We've got the ability to play around with those requirements. So what if we change the requirements? What impact does that have on those simulations that we're running at a very early stage? We've got the ability to put different options in here. So maybe different wind farm suppliers or turbine suppliers, the different performances of the turbines, and capture different trade studies that meet or don't meet the requirements. It gives us a guide to what to take forward to examine further. Here you can see now running trade studies, really early trade studies, running in this case only 14 days, but we can run years worth of trade studies that give some variability to in this case the solar farm, the battery sizing, the wind capacity, wind turbines that provide different outputs, and then automatically capturing those as part of the trade study. So that's the first part. That's model-based, sort of that model-based systems engineering approach. And of course, part of that is then development of requirements. And here you can see that model that's presented within our 3D Experience platform, and the sharing and synchronization of requirements that come from those early studies, and give access and the management and life cycling of those requirements to everybody else within the project or within the development project. So it gives visibility of those requirements that can then be worked on further. Another part of the development, bid development is from a geospatial, geographic point of view. And here we've got two different options that we're exploring as part of this bid. So these bids, which of these options is going to provide us the most viable bid to take forward? Here we're looking at not only the GIS information, but potentially subsurface, but also product. So in this case, potentially reusing hydrogen storage, or it could be really early space allocation models linked to the product breakdown structure or plant breakdown structure for each of these different opportunities. Layering up this information gives access to environmental conditions. We understand maybe shipping lanes, we understand undersea cables, areas of restrictions and constraints that we've got to deal with, and it allows us to examine all aspects and gives all stakeholders the ability to visualize this information in a single referential. Let's move on very quickly. And again, for this first part, another aspect is when we're trying to develop a bid, we want to understand different developments that are going on, different innovative technologies, if I can put my words out. So here we've got sort of social listening, access to live web pages based on different themes of information that we're interested in. We've got some AI technology that's being developed in this to automatically capture the new technologies that have been presented and developed from different partners, and we've got the ability then to share those as different ideas within our community for a whole community of engineers and project personnel to collaborate on. So that's one aspect of that. The new technology and technology readiness levels and ideas that we might want to consider. So ideas from every person who was part of the project, really collaborative, is made available this dashboard, as well as technical readiness levels for innovative technology. So we can get access to see what technology is coming, when do we think it's going to be available, can we include it in as part of our bid? We've got all of those different, the view of that technology. And then from a stakeholder point of view, is who are our stakeholders? Let's consider them and analyze them as part of some standard frameworks. So here we've got a PESEL PESEL framework that we're going to capture information across, and it's very collaborative. We can share this collaborative dashboard with our stakeholders as well to sort of capture their needs, wants, expectations from the project as well, from the bid. So we're absolutely sure we're not missing anything that we need to provide to those stakeholders, environmental conditions, etc., environmental considerations that we need to capture. And we've got this collaborative tool that gives the ability to generate data over many different frameworks, but forms part of the traceability that you'll see towards the end through all of our data. So pass back over to Mark for the next topic.
Thanks, Graham. So moving on to the second point on ecosystem modeling. So by modeling the ecosystem, we are then we're empowered really to make some smart decisions, smart investment decisions to help secure the funds that we need for the project. But we can include financial metrics or criteria or explore the financial viability of a project through ecosystem modeling, and the informed decisions that will allow us to maximize the return on investment, mitigate risk, and maximize the potential for overall success by identifying the most realistic and competitive bids to make sure that they are the correct ones. And a scalable and repeatable approach allows for efficient strategy for modeling assets as well. So Graham will also give some examples on ecosystem modeling.
Exactly. So slightly sideways step here, because we're using a model-based approach, but to model the enterprise and model the ecosystem. So all aspects of the organization itself. So in this organization is, okay, we're transforming our organization, maybe from oil and gas provider or developer to renewables. We want to know what we can or should be bidding on as part of an organization. So analyzing and modeling our own organization gives us the ability to highlight the business drivers, capture business objectives and goals, and challenges that come along with that. So if we're going to bid on certain projects, do we have the capability to do that? What type of projects or bids are going to be the right ones for us to meet our business drivers? And this is a living, breathing model that can be taken forward through the life of the organization, if you like, that captures business processes, business workflows, as well as all the aspects of capability. Here you see as a result of some capabilities, there are requirements being generated for capabilities. We've got a list of capabilities that we need in order to bid for renewable energy projects, if you like. So we're really capturing the organization, the supply chain as well. The robustness of our supply chain can be modeled to include those within absolute must as to understand what the local supply chain is capable of. And then to model theoretical or agnostic projects to understand and test out our thinking in terms of an enterprise, and connect the resources of projects, identify what types of resources we need. Are we still able to compete and to have we the capability to bid on these types of technologies that we want to explore? So it's an enterprise modeling using a framework, a regulatory framework that enables all of our system engineers to model at the right level of fidelity. It connects the projects back to the organization and to validate the capabilities of that organization. Pass back over to Mark for the next point.
Thanks, Graham. So the last point, really, advanced logical, functional, multi-physics simulations. So even at the earlier project assessment stage, we can start to evaluate some of the more detailed technical aspects that will impact the business. So multi-scale, multi-physics, considering data by physics and scale, for example, temporal or spatial scales, how they affect things, how their interdependencies. So it could be hydraulics, aerodynamics, salinity, icing, acoustics, thermal, electromagnetic effects affecting array cables, connections, geotechnical, for example, design, exploration, optimization, with the goal of fail fast, learn quicker, so we can find the optimum position quicker. And how do these affect our bid and our commercial impacts? Can I use data science to predict weather effects to affect my power takeoff commitments, for example? So yeah, go over to Graham for some examples on this.
Yeah, so we've started around that funnel. We've taken a number of project opportunities. We've started to model them from a financial viability. Now we're looking more of a technical. We've filtered down a few that we want to explore further. And we've got the ability to create a digital object called a process composer workflow. In this case, this object in the center that connects models, tools, scripts together in a workflow and a design of experiments. And they can be Dassault tools, models, scripts, or they can be external tools. And we can connect those together to, one, maximize the return of investment on the tools that you already have in your organization, but connect them and run thousands of trade studies. In this case, we've got a foundational model. You saw the layout, optimized layout, and parametric layout of the wind farm. For each of those positions, we're taking the geology models and the layering up and parametric layering of the foundation, what's going on below the surface, or it could be a wake steering model or a wake model. Also behavior models. So the behaviors, system behavior models can be included in this loop and connected within this loop to explore many different thousands of variables, use cases that then bring thousands of results. So in this case, we've run 400 different design studies that collaboratively we want to explore. The system has automatically ranked the scoring, but we can choose to prioritize or to increase or decrease the objective of a number of those different parameters, which is re-ranking the results here. So we're really exploring those thousands of trade studies collaboratively. Those results sit on our database. So if there's any changes within the workflow, within the requirements that initiated these results, is very quick to actually rerun them and re-evaluate. So we're given access to many different graphs, many different visual representations of the results to explore. Those, again, this is just one single use case that connects a number of tools together, a number of parametric models, but there's thousands that we could talk about. But the key thing here is the collaborative nature and the ability to compare these results side by side and really take some robust decisions about the concepts that we want to explore further or take into the next level of detail. And it really connects the stakeholders in to capture all these, and ultimately generate a more accurate and robust set of requirements at the end of this. So just fast forward slightly, we're going to generate those requirements that again can be shared within the platform. So all parties, all collaborators have access to those requirements and their parameters that can be used directly within some of our tools. One last video that I'm going to just talk about is traceability. And we've got the ability through everything we've spoken about so far to provide, get this video going, end-to-end traceability. So through all of our models, in this case, a functional, logical, so your product breakdown structure to the physical in this case, which is, it could be CAD, it could be space allocation models, and the ability to cross-highlight from the requirement, the earliest requirement, through all of these models and more, to the virtual twin and impose that data onto the virtual twin. And again, these can be external models. They don't have to be Dassault Systèmes. We're not trying to force you down the route of Dassault tools, but there are added values, of course, of using our tools directly. So we've really got an end-to-end view. And I'll pause there. Sorry.
Great, thanks, Graham. So I think culminating then, we just wanted to thank you for your participation here and also let you know about a digital storyboard for wind that we've also developed. And this has a lot of assets in there, and some of the movies that Graham also showed are available in here for everyone. So if you want to get access to that, you can contact Graham and I, and we can give you access to this webpage, which runs through many of the movies that we showed as well. So yeah, so
brilliant.
Great. Thank you very much, Graham.